And then what we have to do is we just consider the whole neighborhood of the test instance. Okay? We just sum up all the evidence from the neighborhood because we consider the IID sample, so you can have this big sum here, sum up the whole every instance in the neighborhood. And then, as you can see here, we denote this second part with omega plus. So basically, this omega plus is just evidence for positive class, within the neighborhood. And this omega zero is a biased term, or you can also consider it as a prior probability in a sense. Okay? So, if you look at it, statistically you look at it, you find out that this formula is nothing else than conventional logistic regression equation, right? And the idea is, if you take nearest label principle and you apply base inference, then you come down to realizing this nearest label with logistic regression. All right? Okay. So let's just copy this formula in the second slide. So it's the same thing. Let's say watch this problem from different number. So far we talked about distance, but actually you can also consider this from a different number in terms of similarity. Distance, similarity, correspondingly. So actually you can consider this part. Instead of distance, you can define a similarity function between distance. So in this sense that you can apply any similarity function you want. You can apply kernel if you want. Okay? In fact, by doing this, we can include the standard, say, KDML approach as a special case. What we have to do is we just set omega 0 to 0, and we define a special kernel in this formula, which is if the instance in our neighborhood is 1, otherwise the similarity there. If we define this way, we can include the KDML as a special case. Alright? So, this is so much for the single level case. And then let's consider multi-level case. Actually, the idea is the same. We consider the neighborhood labels as extra feature. So, when someone asks, does he like basketball? We consider the information for all the labels in the neighborhood. So basically, we got an extended representation in the following way. So similarly, this means that 1 among 3 neighbors like table tennis in this instance. Okay, this is extra features. So now, what you have to do is, you only have to solve one logistic regression for each single label. Okay, for example, if you ask, does this guy like basketball? Football. Does this guy like football? Then you just look at this equation. Okay? And you just solve this equation using logistic regression. The nice thing is, this alpha parameter which you got from logistic regression can tell you the appearance of this basketball. How does this appearance of basketball influence on this one's hobby on football? Right? It's very easy to interpret. Okay? And this omega plus is just evidence which you got from the neighborhood. Alright? This is very nice because you can interpret the whole model very easily. Just for the sake of completeness, I wrote down this decision rule for you then. For multilabel prediction rule, you just consider the sign of this duration. And if you want to output a ranking, you, instead of considering the sign, you consider the score of this function. Okay? So this is the decision rule. Now I start to talk about some parameters results. And all these data are multilabel data sets. So we really try hard to find this many multilabel data sets because it's not so easy to find multilabel data sets. And it's coming from different domains, from music, computer version, biology, and so on. And we have tested on the following different approaches. Of course, we compare with similarity-based, because it's also instant-based approach. And we also take another approach as a baseline, like the Banner relevance with logistic regression, simplified KNN is base layer. And label power side is another baseline in terms of labeling. And of course, we also test on our approach, idea around ML. And I want to say this is that for the sake of fairness, we set all the parameter settings the same as ML. So actually, it's only one parameter, it's the number of k for the nearest label. We set the same as ML, which is, by the way, 10. The 10 is the value which is suggested by this ML in this paper, because the 10 leads to best result of ML. So for the sake of fairness, we set the same as ML. And we test on different, say, loss function or say different evaluation metrics for this multi-label learning. And I just wrote this definition here for sake of completeness. And actually, I just want to say the reason we take all this metrics is because it was also used by this American paper. So again, for the sake of fairness, we're using the same evaluation metric. And we have done a two-step statistic test. In the very first test, we apply a Friedman test, which to reject the null hypothesis that all the classified performance equally. Okay, this is the first test. We want to find a difference among all the methods. And the Friedman test successfully rejected the null hypothesis. And then, as a second step, we apply this pairwise test, which is an invention test in this case. So we test all the different methods in a pairwise way. So here are the results of the dimension test in the big table. So actually, you will see that this is the rank for all the methods for each different metric. As you can see here, even though we have 7 data sets, it's quite a lot for the label classification. But from a statistical point of view, it is still a very limited number. So in the test, we have some problem to find statistical significance. But nevertheless, the big picture is very clear, right? I mean, we almost always, actually we always is the first one. And consistently outperforms the American and other baseline. So this is the big message, correct? Yeah, I'm pretty much done here. I want to wrap up with some conclusions. We have proposed a new approach to instance learning. Even though we have applied it in the multi-label setting, but actually this approach can be applied for classification in general. And the key idea is rather simple. We consider the label information in the neighborhood as an extra feature. And by using logistic regression, we balance between the global and the local inference. Basically, the two parts is one is the bias term, another part is evidence from the neighborhood. We balance it with logistic regression with the parameter alpha. And the way we do this is, when you're using this approach, you can take the correlation between labels into consideration. I think that is the major reason why we can outperform the American on a large scale. And of course, in the paper, we have some other extensions. Like, for example, we also combine these normal features, insta features together. But I won't go to details here. So if you're interested, you can check the paper. And one last thing I want to say is, this approach is now publicly available in this Mulan Java library. Mulan is a multi-label classification Java library, open source, and which is maintained by the machine learning and knowledge discovery group in the University of Thessaloniki. And if you want to know more information, you can just check my website. And you are welcome to try our approach in this Mulan package. So this is all from my side, and I would like to answer your question. And if you have any comments.